Structural Steel Design by Engineer Francisco R. Onde Jr. Hello everyone, welcome back to my channel. This is On The Reel, and in this video we'll be discussing how to calculate the nominal compressive strength of a W-shaped column without a slender element, and also the LRFD Design Compressive Strength, that is load and resistance factor design, and also the ASD Allowable Compressive Strength, the allowable strength design. And also, we are to calculate safe service load that the column can carry if there is a given service dead load. Okay, let's start now. But before pala, please, if you have not subscribed yet to my channel, please do so. Okay, so here's the question. Determine the nominal compressive strength of a W360 by 110 A992 steel column having a length of 6 meters and pinned at both ends. The minimum yield stress is 345 megapascal. So these are the geometric properties of the W shape given, and this is the shape. So how to solve for the nominal compressive strength? I'll be discussing how to solve it in details. First, this is what you're going to do. Calculate the limiting width to thickness ratios. According to the code says that for uniform compression in flanges of rolled I-shaped sections, plates projecting from rolled I-shaped sections, or an outstanding legs of pairs of angles in continuous contact and flanges of channels, the width to thickness ratio B over T is 0.56 square root of E over Fy. This is the limiting width to thickness ratio for a non-slender element. If the width to thickness ratio exceeds this, then the member is said to be a slender element. Okay? But if the width to thickness ratio doesn't exceed this, then it's not a slender element. It's either a compact or a non-compact. So for the flange, it's 0.56 square root of E over Fy. So solving for that, E is 200,000, of course, for steel, and Fy is 345, and that will give us 13.48. Then after that, calculate the limiting width to thickness ratio for the web, the stiffened element. Okay, so for the web, that is 1.49 square root of E over Fy. Okay, that means if this B over T or H over TW exceeds 1.49 square root of E over Fy, then that means that member is a slender element. That means its ratio width over the thickness is too large. Okay, so if ganyan, then it would be subject to a local buckling before it will fail sa general buckling. Now, so that is 1.49 square root of E over Fy, and evaluating that, we get 35.87. So let's calculate the width to thickness ratio of this given W shape. And that is, for the flange, that is half of the width of the flange over the thickness of the flange. It must be of the flange. Okay, so solving for that, that is BF over 2TF, and that is 257 given over 2 times 19.9, and that will give us 6.46. Now, this is less than 13.48. That means that flange is not a slender element. Okay, so it won't fail sa local buckling. No? Web. For the web, it should be equal to H over TW, where TW is the thickness of the web. Now that H is equal to D minus 2K design. That K sub des or K design is the design distance from the outer face of the flange to the web toe of the fillet. Okay, so dito yan. It must not be just TF but the KDS. So that is D, the total depth, minus twice of KDS. and that will give us 361 minus twice of 35.1 millimeters over 11.4, and that is 25.51. And that is still less than this limiting width to thickness ratio. Okay, and that means the web is not a slender element. So since these are not slender elements, then we can calculate the nominal strength for the flexural buckling using this provision now given by the NSCP 2015. So for flexural buckling without slender elements, the nominal compressive strength Pn shall be determined based on the limit state of flexural buckling. So P sub n is equal to FCR times Ag. FCR is the flexural buckling stress, and Ag, of course, is the gross area of the W shape. So that flexural buckling stress is determined as follows when KL over R, or that is the slenderness ratio, is less than or equal to 4.71 square root of E over Fy, or the elastic critical buckling stress, or the Euler critical buckling stress. If it exceeds 0.44 Fy, then we're gonna use this formula, that is FCR equal to 0.658 raised to Fy over Fe times Fy. When K over L, or the slenderness ratio, exceeds 4.71 square root of E over Fy, or that Euler buckling stress is less than 0.44 of Fy, then we must use 0.877 Fe. Or pwede rin, if the ratio of Fy over Fe is less than 2.25, then we're gonna use this. If the ratio of Fy over Fe exceeds 2.25, then we're gonna use this. Okay, so this Fe is again the elastic critical buckling stress, or the Euler buckling stress. That is Fe is equal to pi squared E over KL over R squared, or the slenderness ratio. And that slenderness ratio must be the maximum. Now, comparing the slenderness ratio with respect to the strong axis, or x-axis, and the slenderness ratio with respect to y-axis. Well, apparently, we're gonna use the KL over R with respect to y-axis dito, because the radius of gyration, the minimum is the R sub y. Okay, so let's proceed calculating the limiting. So 4.71 square root of E over Fy, and that is equal to 113.4. Now, let's calculate the slenderness ratio, KL over R. So, as you can see, the length is 6 meters, and this column is pinned at both ends. Based on AISC, or the NSCP, we're going to use K equal to 1.0 for pinned connection at both ends. Okay, and the R that we must use is the minimum, 63 millimeters. Okay, ito yun. And the KL over R is 1 times 6,000 over 63, and that would give us 95.24. Okay, now this is less than 113.4. That means its kind of failure must be the inelastic buckling. Okay, parang ganito yan. If we are to graph this, no, this is the buckling stress that we're going to use, the FCR. So the 4.71 square root of E over Fy, that's here, 113.4. So dito, that belongs to the inelastic buckling region. Well, dito, after that 4.71 square root of E over Fy, the failure would be the elastic buckling. So here, we're going to use FCR is equal to 0.658 raised to Fy over Fe times Fy. Okay, so calculating the elastic critical buckling stress, or the Euler buckling stress, so that is pi squared E over KL over R squared, and that is pi squared times 200,000 megapascal over 95.24, and that will give us 217.62 megapascal. After that, we can now calculate for the flexural buckling stress, FCR. So again, using this formula, since KL over R is less than 4.71 square root of E over Fy, so substituting this, 0.658 raised to the ratio of 345 over 217.62 times Fy, which is 345, that will give us 177.68 megapascal. So with this, we can now calculate the nominal strength, the one that is being asked in this problem. So the nominal compressive strength Pn is equal to the product of the flexural buckling stress FCR and the gross area A sub G. So multiplying them, 177.68 times this 14,100 squared millimeters, that is equal to 2,505,288, and that is in newtons. So in kilonewtons, that is 2,505.3 kilonewtons. That is the nominal strength. Okay. Now, after that, how about if we are to calculate the design compressive strength according to LRFD and also the allowable compressive strength according to ASD of this white flange? How to calculate this? So since we already got the nominal strength, we know that the LRFD design compressive strength is equal to the product of the reduction factor phi sub c times the nominal strength p sub n. So the design compressive strength is phi pn. Now, so for compression, phi is 0.9. So that is equal to 0.9 times 2,505.3, and that will give us 2,254.77 kilonewton. That is the design compressive strength. Now for the ASD, the allowable compressive strength must be equal to the nominal strength over the factor of safety 1.67. So that is 2,505.3 divided by 1.67, and that will give us 1,500.18 kilonewton. Now, what do this mean? Well, this means that dapat this design strength must be greater than the factored load. Okay, so it must be greater than 1.2 dead load plus 1.2 compressive live load. Okay, now according to ASD, this allowable compressive strength must be greater than this required strength. Now, this is the required strength, PD plus PL. Okay? So, yan yung ibig sabihin yan. Dapat, it must be less than 1,500. Na pwede 1,400, pwede exactly 1,500. Okay? Pwede ganun. So, if we are to calculate this, last na tayo, determining the safe service live load that this column with a nominal strength of 2,505.3 kilonewton can carry using both the LRFD factored load combination and the ASD load combinations if the service dead load is 360 kilonewton. Okay, this is the service dead load, P sub D. Now, kanina, we got the LRFD design strength equal to 2,254.77. So this must be greater than the factored load required strength 1.2 PD plus 1.6 PL. So if we are to substitute, PD is 360 as given, and solving for PL, okay, transfer to the other side, then dividing by 1.6 both sides. So that service live load, compressive live load, must be less than or equal to 1,139.23. It must not be greater than that. Pwede 1,100, pwede 1,000 kilonewton. Okay, for it to stay safe. Now for ASD, from a given or from the solved design strength, okay, or the allowable strength, Pn over omega C, or the factor of safety, 1,500 kilonewton, it must be greater than the required strength. Okay, so the required strength for ASD is just the sum without factors. So PD plus PL. So solving for PL, that PL must be less than the difference of 1,500.18 and 360. And that is 1,140.2 kilonewton. As you can see, malapit lang, no? about 1,140. So if there are choices, if this is a problem in the board exam, if there are choices, say the choices are 1,000, 1,100, 1,200, 1,300, better to choose 1,100. The 1,000 kilonewton is also safe, but the maximum it can carry among the choices is 1,100. Now, you must not choose 1,200 because it would fail. Okay, both considering LRFD and ASD. Okay, so that's it. That's how to calculate the design strength considering LRFD and also allowable strength considering ASD using NSCP 2015. In my future video, I'll be discussing how to calculate these strengths, design and allowable compressive strength, if there's a slender member. Now, what is slender member? That means the thickness is too small compared to the width. It's like this. Suppose if I'm gonna extend this, let's say the width of the flange is ganito. Draw first. So ito yung width of the flange. Okay? Then as you can see, it would probably buckle, local buckling. Yan yung local buckling. Before it will fail sa general buckling. So with that, it would be including reduction factor Q in calculating for the nominal strength. Okay? So that would be in the future video. So I hope you like this. Okay, and if you do like this, please click that like button and also leave some comments now for me to be encouraged to post more discussions about um, 2015 NSCP. Okay, so thank you. Hopefully you have subscribed already in my channel, and hopefully you would share this to others. Okay, so thank you for everything. Thank you for listening. See you guys next time. Goodbye and God bless.